So in the previous class, we were talking about different types of material properties and characteristics. We talked about fatigue behavior, what is high cycle fatigue and what is low cycle fatigue. We also talked about different classifications based on yield stress versus the ultimate stress. So the steel that we often know as Fe410 can also be referred to as E250, correct? Here. And various constituents of steel and so on. Now, one particular slide, which is actually in your lecture notes, it is coming much later, but today I was going through it and I felt like this belonged somewhere here before I get into the discussion on failure theories, etc. So so we have talked about thermal elongation, right? Thermal elongation, we had a small discussion that if you have a bar which is restrained at both ends, it will only take a temperature rise of 100 degrees centigrade to make that bar yield completely on its own restraint forces, right? And also we talked about toughness. So these are the two properties that are affected significantly by temperature. We had a large amount of discussion on that already, right? Thermal elongation, of course, it depends on temperature, and toughness, that also depends on temperature. Another material property of steel that depends on temperature is creep. So who can tell me what creep is?
Sir, creep is the long-term deformation of the concrete.
Yeah, long-term deformation of any material. So can you, one second, 1% at a time. So Gajendra, right? That's your first name, Gajendra?
Yes.
Or is it Sajal?
No, Shayan is the first.
Shayan. Oh, sorry, Shayan. So Shayan, long-term deformation, you are right. Under what conditions? Will you call shrinkage as creep? Shrinkage is also long-term deformation, right?
Yes.
Shrinkage in concrete, is that creep too?
No, sir.
Is that a type of
it's different.
It's different. Why is it different?
It's under sustained loading.
Good. Yeah. So, Krishna, so if anybody wants to say something, you can kind of, if I'm talking to one person and the other person wants to intervene, you can kind of raise hand or say something like, I want to answer it. Krishna. Fine. So yeah, so it is under sustained loading. Leo wanted to answer that. I stopped him. That's why I'm saying this. Yeah.
Okay, sir.
So I think you had the similar answer, right, Leo?
Yes, sir.
Yeah. So under loading condition or under mechanical loading condition, not thermal loading condition, or not under just time it on its own does not cause creep. Under stress, so then you may have creep under stress if you leave the material for long durations, long time under a sustained load level or some sustained stress level. Another manifestation of this creep reflects in pre-stressing strands. What do we know? What do we call that? The pre-stressing strands relaxation. Yeah, so they tend to relax, and relaxation is a more complex phenomenon because they are wound cables. So the relaxation is not simply the creep effect; it is also somewhat unwinding of those things, or So because of that winding effect, you have for a long period of time, if you keep it stressed, that leads to some kind of a relaxation. So it is not purely creep effect, but yeah, I mean, it has similar feel, in so to say. Okay, steel in general, we don't worry about creep, right? But when you heat it at high temperatures, like heat it to temperatures of the order of 300 or above, 300 degrees centigrade or above, then what you see is that even steel starts to behave as if it has some creep deformations. And basically, creep is basically a viscous kind of a property, right? Viscosity is what is time dependent, right? So in mechanics, mostly we assume springs to have a deformation which is related only with force, correct? So deformation is related with force. The other force that may have a role to play is the viscous force, wherein the velocity depends on the force, right? So if you apply a certain amount of force, it will exert certain amount of velocity, and velocity is a time-dependent parameter. So as a consequence, your deformation becomes time-dependent. So for a given amount of force, your deformation becomes time-dependent, and that you can see very easily in which materials? Plastics, right? Plastics, resins, those kind of materials have polymers. They have a lot of creep deformations. Concrete also has significant amount of creep deformation. Steel at ambient temperature does not have it so much, but at elevated temperatures, it also has creep effect. And also, if you heat it beyond 400-500 degrees centigrade, then, so that is typically your fire scenarios. If you are working with structures in fire, then your strength and elastic modulus also start to decline beyond 400 degrees centigrade. Strength starts to decline quite significantly. So that also has a role to play. I'll not spend too much time on this one. That is my primary area of research, but if you're interested, you can always discuss with me later. I'll move forward in this class. So yesterday, in the previous class, we had talked about that we will discuss when does a material fail, how to define the material failure, right? So we had, like, first of all, what is failure? Failure is a very generic term, right? So we may define what we call failure. Okay, so I may call failure of a material when the yield stress, when the stress in the material is 60% of the yield stress. So I take a coupon. So in the previous class, we had talked about this coupon that is cut from a plate. So let's say if you have a plate or if you have a rod or whatever. So you may, if you have a rod that you want to test, then you typically make a dog bone shape, which is 3-dimensional. If you have a plate, then you make which is only 2-dimensional. So it is more of a prismatic shape. Okay. So you take a coupon, you test it in the lab, and you can define the failure. My failure limit could be something else, your failure limit could be something else. But some of the most commonly used failure limits are such as yield stress or ultimate stress. So if I want to define the yield stress of a material, it's very easy to do it, right? So you take that coupon, test it in the uniaxial direction, you will get a plot somewhat like this, right? You must have all seen this kind of a plot in your UG labs, right? Construction materials lab. So the first point here, where the material stops, especially mild steel, when it stops becoming linear, you call it yield point. Right? Then you have upper yield and lower yield. Then you have a somewhat of a plateau. Then you have a gradual increase in the stress, which is called strain hardening portion. And then you have a ultimate strength or tensile strength. And at some point, at some certain amount of deformation, you have failure. And this deformation or this strain value is known as the, what is it? Is it known as?
Fracture point.
Maximum deformation or ductility. It's a measure of ductility. Yeah. That point is called failure or fracture when it splits, but that corresponding deformation is called maximum deformation or maximum elongation. Okay, so when you want to buy a steel, you have to also look for that property. So for example, if I am buying a E250 steel of A grade, I will be looking for a ultimate tensile strength of 410. If depending on the thickness of the plate, so these are the thickness values, 20 mm, between 20 and 40 mm or more than 40 mm. Then this should have this much of yield stress, 250 MPa, 240 MPa, 230 MPa, and so on. And then percentage elongation. That is that 23%. So this is strain. This is strain minimum, it should have at least 23% strain before it ruptures. Okay, and that strain is measured over the gauge length. It is not the entire bars, entire coupons. It is not the elongation of the full coupon. It is the elongation of this gauge length. Okay, so that is easy. And so let's say we call yielding as the limit state or the failure criterion, and you can very easily get a yielding point through this test, and you can say, okay, this is the limit state. This is the failure definition. Wonderful. No issues. It's very easy to test. Almost every institute has one such lab, one such equipment where they can test it. Now, what is the challenge? The challenge is that if I have a complicated geometry, let's say I have a crankshaft, right? And I want to know under what stress will it feel? At how much force can I apply on that crankshaft? At which point this crankshaft will start to yield. Now the stress state is not your coupon stress state. In a coupon case, you had a uniaxial tension. Now you've got a very complicated stress state, and we want to know when is the yields, when are we reaching the yield point, right? And that is where these failure theories come into picture. So before we get into the failure theories, before we go into the failure theories, there is something called invariant, right? Are you familiar with some kind of invariants? Have you started taking class on elasticity, plasticity? Students, are you listening?
So only one class has happened, but just started.
Okay, so what was taught in that first class?
Just
So the
Stress tensor, strain tensor, Hooke's law. Something must have been started, right? Something must have been taught. No?
just
So
the
it was an introductory class because most students haven't registered back then.
Okay, they had not registered. Okay, fine. So, but anyway, I'm sure you all are familiar with the concept of principal stresses. You all know what principal stresses are, right? So those who went through an interview, they of course were asked such questions, and those who have come by a gate, they must have learned these principal stresses anyway. So principal stresses are some kind of invariants. Have you heard of term invariant in structural mechanics? Invariants, no?
No, sir.
Let me write it. Invariants. No? Okay. So I don't have a very nice graphics to present here, so I'm sorry, you have to look at my gestures of my hand. So follow my hands, huh? And if you are not able to understand, ask me again. So you are all familiar with the nine components of stress, right? So if I have a three-dimensional space, can you see the screen?
yes, sir.
Yeah. So this is a three-dimensional space X, Y, Z, and you have certain stresses in this, and you have some, let's say, some element here. Okay. So and actually, this element is not a full body on its own. It is basically a bigger body. There, I have taken a small element inside that body. Okay, and I'm looking at the stresses. So I zoom in, and let's say at a time I'm looking at only one plane. I'm ignoring the Z components. So what you will have is sigma xx here. You will have sigma yy here. Okay, and similarly on the other face, and then you may have sigma xy. I'll call it sigma xy. You can call it tau xy also. It's your call. Right? Fine. And how is this produced? Because this small element was part of a bigger body where some forces were acting. Right? So this body is fixed in the space. It is not moving. Okay, I'm not rotating or moving or anything. And these forces that are acting on this potato-shaped body, those forces are also not changing. And I have randomly fixed this XYZ coordinate. I have chosen that. And I have picked an element at a particular location, which is aligned with XYZ, right? So this direction, that is this direction, is parallel to X. This one is parallel to Y, and this is parallel to Z. Fine. That is my call, right? And if I do that, the body will have these stresses, sigma xx, sigma xy, sigma yy, and so on. Fine. And then there will be, so I've got 3 components already. Totally, there will be 9 components. I'm sure you are familiar with that. You must have seen this matrix. See, sigma xx, sigma xy, sigma xz. Likewise, here you will have sigma yy, and here you will have sigma zz, and sigma yz, and then this is symmetric matrix. Okay. Excuse me for my very poor penmanship. My handwriting has never been good, and with this new tool that I'm using, it is even worse. I hope you can still read it, right? Okay. So this is called stress tensor. You will be taught this thing in much more detail in your elasticity course. Sorry. It has 9 components. You can see the 9 components, right? So this part is symmetric. So out of the 9 components, you have 3 normal stress components, xx, yy, zz, and then you have 3 shear components, which are also reciprocal on the other side. So total 6 shear components. Fine. Now, these sigma xx, yy, zz, and sigma xy, sigma xz, all these values are for this small element that I have selected. This particular element that I have selected, isn't it? Agreed? Yeah. So now let's say,
Yes, sir.
yeah. So now let's say I decide to change my orientation slightly, and I move in one axis, which is called x prime, y prime. I wish I had used different color, but I am very lazy with picking different colors, and then I mix up them. So I'm continuing to use the same color. So I have just reoriented my x, y, z completely, and I've gotten to my x prime, y prime, z prime. Okay, so this will be y. I should call it z prime. Sorry. Okay. So I have rotated about x by certain degrees, then I have rotated by around y with a certain degrees, then by z, and I've gotten a new configuration. Now what happens, instead of this cube, my cube may be oriented at a different angle, right? I'm drawing it only in 2D, but actually it may rotate in 3D, right? Now what happens for this cube, the stress values that I will get, the stress tensor that I will get will have not sigma xx, but sigma x prime, sigma x prime, y prime, and this will be marked as sigma x prime, sigma y prime, and sigma x prime, y prime. You got the picture, right? I'm not drawing the whole thing again. Sigma x prime, z prime. So now you will have 9 new numbers here. Okay. How did I get in? So this was original stress tensor, and this is the new stress tensor. How did I get the new stress tensor? What did I do to get the new stress tensor? Did I change the loads on the system? No. Did I move the, one second. Did I move the body itself or reoriented the body itself? No.
No.
All I did
No,
was
sir.
I only changed my point of view, or I only changed my reference of, like, point of reference, right? I only changed the definition of x, y, and z. I started calling some other directions x, y, and z, right? So, but just by doing that, I got slightly different numbers for the stress tensor. Does that mean that actually the stress state at that particular location where this element was located changed? Would it have changed just by me changing my direction or changing the axis of x, y, z to x prime, y prime, z prime? They would not, right? Because fundamentally, if you see, the body has not rotated or moved, and the forces have not rotated or moved. They are still there. So at a particular location, the stress state would not have changed. But still my tensor has changed. So what it means is that in these 9 quantities that we see inside the stress tensor, there must be something that remains unchanged, even though I change from here to here. The stress tensor may change from here to here, but there must be some things that do not change, which actually represent the stress state uniquely. You understand? How many
Yes,
of you
sir.
understood this part?
Yes, sir.
Okay, who did not understand?
Yes, sir.
This is a very important part to understand. So, anybody who did not understand, please raise your hand. Just shout out, give me a shout. I'll explain again. I'll try to explain again.
So can you just
Everybody understood, huh? Yeah, Krishna, tell me.
repeat the last 2-3 lines?
Okay. This stress tensor, how I developed, that you understood, right? So there will be a stress tensor like this, and maybe if you don't know exactly how it is developed, you would know it when you take that course on elasticity, plasticity. You are familiar with some of these terms, obviously, right? Sigma xx, sigma xy, tau x or tau xy, sigma yy, and so on,
Yes.
right?
Yes, sir.
So this is the stress condition. If I had used this x, y, z as my reference coordinate system, okay?
Yes,
If I change my coordinate system to x prime, y prime, z prime, my stress tensor looks like this. That is marked here, right? In this coordinate system. Now, what what I have done when I changed from x, y, z to x prime, y prime, z prime is that imaginary coordinate system that I have created. So for example, this element that I have picked, which is infinitely small element in the material, and I'm looking at the stresses in that element, I have decided which orientation I want to look at. So this small cube, I have rotated this way at the same location, or I have rotated this way, or rotated it this way, or rotated it this way. I can rotate it the way I want. But if you think from materials point of view, the body has not moved, the forces have not moved. So at that particular location, the actual stress state should not have changed, because the stress has something to do with the force equilibrium, etc. It does not depend on how I am looking at it. So whether I'm looking at it from here or here or here or here, it should not affect the stresses in that location. But these stress values are getting affected. They are changing just because I changes my orientation. So what it means is that even though these individual values might be changing, there must be something in this matrix that should not be changing, which should be representing the stress state. And those things are called invariants. Okay. One such invariants are, now it will click, principal stresses. Okay. There are more. Even maximum shear stress, that is also one invariant. Okay. So why is principal stress an invariant? We will look at more circles. Okay. I hope even if it is not 100% clear, maybe when I explain the principal stress, it will be clearer. But I mean, you must know principal stresses already. So this is one element that similar to one that I was showing you, and it has stresses sigma xx, sigma yy, sigma y xy. Okay, as shown here. Any questions? Okay. So this is the stress state, and we know how to draw the Mohr circle, right? So for this phase, we take sigma xx, sigma xy, we draw it here. For this phase, we take sigma yy minus sigma xy, and we draw it here. Okay. The two faces are at 90 degrees from each other. So we call it 180 degrees on the Mohr circle. Then the Mohr circle is drawn around by keeping these 2 points in the diametrically opposite locations. So the Mohr circle looks somewhat like this. Agreed? You are all familiar with Mohr circle, right? And these 2 locations, these 2 points, these are called the locations of principal stresses. That's where you don't have any shear stress. And there always exists one orientation where there is no shear stress. That is called principal stress. Okay. So these principal stresses we will call sigma 1 and sigma 2. And they exist in a particular orientation. So if the original element was oriented like this, let's say, and so basically that is our definition of x and y. This is the definition of x, this is the definition of y. And that was the stress state. If I change my definition of x and y to these and this, or rather, sorry, this is my x, new x, and this is my new y, then your sigma x and sigma y will be these stresses. And in this orientation, the stresses are sigma 1 and sigma 2, or sigma x and sigma y. Agreed? And you don't have any shear stress, right? So these principal stresses uniquely define the Mohr circle. And it is the Mohr circle which uniquely defines the stress state. As I'm changing my orientation, you remember that orientation thing? Whether I'm taking x, y, z as the coordinate system or x prime, y prime, z prime as the coordinate system. As I'm changing my orientation, all I'm doing is I'm moving on this Mohr circle. But the Mohr circle defines the stress state uniquely, completely. And one such way to define the Mohr circle uniquely is to just know the values of sigma 1 and sigma 2. So if I know the value of sigma 1 and sigma 2, I can define the Mohr circle uniquely. And then that point onwards, no matter which orientation you are in, you will be still describing. So your individual values of sigma xx, sigma xy, sigma yy will keep changing as you keep traveling on this Mohr circle, but you will be representing the same stress state, the same stress at that point. Only thing is that your values will keep changing, sigma xx, xy, and yy. But they will be related to each other in such a way so that your sigma 1 and sigma 2 remain unchanged. And so will the tau max will remain unchanged. Okay, so that is why these things are called invariants, right? Because they uniquely define the stress state at that location. They don't vary with the angle, so to say. So principal stresses are one type of invariance. There are more types of invariants. Okay, I hope it is clearer now, right? Prithvi, oh sorry, Krishnan.
Yes, sir.
Yeah. Okay. Good. So we all know how to calculate principal stresses, and now you also know why we call them invariants, because they don't depend on the orientation. No matter what orientation you pick, for this particular element, whether you pick this orientation or you pick a different orientation, or you pick this. Why is it not drawing? Yeah, whether you pick this orientation or you pick this orientation or you pick this orientation, right? Your sigma 1 and sigma 2 values will not change. That is, your principal stresses will not change. That is why they are called invariants. Okay. So now there are a couple of examples. I've shared these in the lecture notes, so I'm not going to go into those. There are shear stress only invariants, how to calculate principal stresses from different situations. This is usually done as an exercise for undergraduate students. I'll not repeat it here. So we all know how to calculate the principal stresses, right? Now comes the question of how to uniquely tell when a metal or a material yields. So we know that when you have a coupon and you test it in tension, it yields when you have that kind of a plateau. When you have that kind of a plateau in the stress strain plot, that's when it yields. And I call that, let's say, Fy. This is from uniaxial tensile test. The question is, when you have a complicated problem, as I was giving an example of a crankshaft or some other kind of a problem, then how do I define when the yielding will happen? Because then the stress is not uniaxial, when it is more complex, right? So I have both. I may have sigma xx, sigma xy, sigma yy, sigma xz, sigma yz, sigma zz. All these components will be present, which are like 6 unique stresses. Okay, so they are all present, and from there, how do I know when the yielding takes place? Because it will take place when a combination of them reaches a particular value. So there are certain theories that people came up with, and these theories don't really have any fundamental reason to rely on. It's just, these are just theories which have been proven through experiments, but they are not derived from any fundamental first principles. Okay, so the first such theory, which is applicable for yield for ductile materials, is known as Tresca criterion. Okay, so this is called Tresca criterion, and it was proposed for metals. I think most of the experiments were done on aluminum. It is also known as maximum shear stress theory. So what the theory basically says is that, you know what is the principal stress sigma 1 and sigma 2, the difference between sigma 1 and sigma 2, the two principal stresses? So this is sigma 1, this is sigma 2. The difference between them is twice the maximum shear stress, right? That is the diameter of the Mohr circle. So the maximum shear stress is half of the difference between sigma 1 and sigma 2. What it says is that you take the difference between sigma 1 and sigma 2 and take the difference between sigma 2 and sigma 3 and take the difference between sigma 3 and sigma 1. You take the modulus so that the signs are removed. So you don't know which one is bigger, which one is smaller. So irrespective of that, you just take the modulus, that is, keep it positive. Take half of that, and whichever one is highest, that should not exceed a particular value. If it exceeds a particular value, that's when the failure happens. Okay, did you follow? So what is the difference between sigma 1 and sigma 2 is half? What is that value? Half of the difference between sigma 1 and sigma 2?
Maximum shear stress.
Maximum shear stress in 1-2 plane. This is the maximum shear stress in 2-3 plane. right? These are principal stress planes. Again, let me go back. Okay. So my XYZ plane was, let's say this is X, this is Y, and the Z is outside the board. And then if you transform it to get the sigma 1, sigma 2, then maybe you will end up with this axis. So this will be your one plane, this will be your two plane, that is principal stress planes, principal planes, okay, principal axis. And then you will have third also. The third will be in some other direction, okay. So what it says is that you take the maximum shear stress in 1, 2 plane. This is one principal plane or one couple of principal axes. Maximum shear stress in 2, 3 plane, maximum shear stress in 3, 1 plane. Take half. So after half, it is maximum shear stress. And then wherever you have maximum shear stress as a net of the 3, that should not exceed a particular value. And when that reaches a particular value, that's when the failure or yielding takes place. Okay. And how will you get that particular value, K value? You can get that from a uniaxial test. Okay. So let's try that. So let's say we do a uniaxial test. When we do a uniaxial test, and let's say our X or one axis is along the axis of the force. So sigma 1 is equal to, when the yielding takes place, what is that sigma 1 value equal to? What is that sigma 1 value equal to when the yielding is taking place?
Fy yield strength.
Correct. So in case of uniaxial stress state, I can substitute Fy for sigma 1. I can put Fy here. But what is the, in uniaxial test, what are the stresses in this direction?
0.
And what are the stresses in this direction?
0, sir.
0 in both directions, because by definition it is uniaxial. So the other axis forces are 0. So I will have to substitute 0 for sigma 2 and 0 for sigma 3. So I put that back into this equation. Maximum of half of sigma 1, 0, and half of sigma 1. So the half of sigma 1 and half of sigma 1, they are both equal. So half of sigma 1 is equal to K. So my K is equal to, and sigma 1 is equal to Fy. So my K is equal to half of Fy, right? My K is equal to half of Fy. So I can substitute that K here. So ultimately this half and this half will cancel out. So I'm left with this equation. So basically what it is saying is that maximum shear stress in 1, 2 plane, maximum shear stress in 2, 3 plane, and maximum shear stress in 3, 1 plane. You take those maximum shear stress, take maximum of all of them, and then when it reaches Fy value, sorry, this is twice the shear stress. I'm sorry, twice the shear stress in 1, 2 plane, twice the shear stress in 2, 3 plane, twice the shear stress in 3, 1 plane. And when it reaches the value of Fy, that's when the failure takes place. That means when the maximum shear stress reaches half of Fy, that's when the yielding takes place. Okay, that is what this Tresca criterion is. And because of this particular finding, we call it maximum shear stress theory. Basically, it is saying you look at all principal axes or all principal planes. You look at 1, 2 plane, you look at 2, 3 plane, and you look at 1, 3 plane. And in whichever plane you have highest amount of shear stress, and when that shear stress reaches Fy by 2, that's when the yielding will take place. Okay, even in a uniaxial loading condition, the yielding took place only when the maximum shear stress reached half of Fy. Fine, is that clear? So let me quickly go to actually this remains until you get a physical graphic representation of this, it remains a bit unclear. I'm not sure if you can appreciate it yet, this particular diagram. Let me move as per the slides only. So basically the criteria says that whenever you have maximum shear stress reaching Fy by 2, the yielding will take place. Now, let's think of some simpler cases. So this was the most generic case where sigma 1, sigma 2, sigma 3, all three of them are present. But let's think of some simpler cases. So let's say, let us have a condition where the stresses are biaxial. When the stresses are biaxial, that means sigma 1 is present, sigma 2 is present, but sigma 3 is not present. Sigma 3 is 0. If that is the condition, your equation will will be simplified to this: sigma 1 minus sigma 2 they will remain. Sigma 3 will become 0, and here sigma 3 will become 0. But since you have mod operation, these functions will remain. Right? So everybody agrees with this? This equation will change to this equation. Sigma 3 terms will go away. So now, if I want to draw that in sigma 1, sigma 2 space, so if I take one axis as sigma 1, the other axis is sigma 2, and I want to draw this geometry. And what it's basically saying is that these are lines. So sigma 1 minus sigma 2 is equal to Fy. That is one line. Similarly, sigma 2 is equal to Fy. That is another line. Sigma 1 is equal to Fy. That is another line. Similarly, sigma 2 minus sigma 1 is equal to Fy. That is another line. Minus sigma 2 is equal to Fy. Another line. Minus sigma 1 is equal to Fy. That is another line. So likewise, you have 6 lines. If I draw one by one, so sigma 1 minus sigma 2 is equal to Fy is basically this line. And it extends, of course. Right? And the failure will happen when this value, sigma 1 minus sigma 2, reaches Fy. As long as sigma 1 minus sigma 2 is less than Fy, that is, you are on this side of this line. You are safe. It is not failed. Once you reach this line, this is that boundary. When you reach this boundary, that's when the failure will happen. Okay, so beyond this, you have the failed material. Likewise, I can draw sigma 2 minus sigma 1 is equal to Fy. Sigma 2 minus sigma 1 is equal to Fy will be this line. And again, the failure will happen when sigma 2 minus sigma 1 is greater than Fy. That is, then you go there, that is failure. But as long as you are inside that line, you are safe. Okay. So likewise, if I draw sigma 1 is equal to Fy, I will get this line. And sigma 1 is equal to minus Fy, or minus sigma 1 is equal to Fy, I'll get this line. And as long as you are within these boundaries, you are safe. Similarly, as long as you are within these boundaries, you are safe. Similarly, as long as you are within these boundaries, that is sigma 2 is equal to Fy, you are safe. Fine? So, as a result, by drawing this geometry, what we get is this surface or this zone of yield surface. And anything that is on the edge of this geometry is called the yield surface. So, as soon as your combination of sigma 1, sigma 2 reaches these values, the yielding happens. And as long as you are anywhere inside, there is no yielding. Okay, that is in sigma 1, sigma 2 space. And sigma 3 is actually perpendicular to this surface, perpendicular to the plane of this slide, this projection. Okay, and sigma 3 we had assumed to be 0. Okay, now that further we can go into special cases and try and look at it. So sigma 3, let's say, remains 0, but now we have another case where sigma 1 is equal to sigma 2. What case will that be? Let's say I have a plate, a steel plate, okay, and it is subjected to some forces F1 here and some forces F2 here. These are uniform forces. I'm just uniform forces applied uniformly over the length. I'm just drawing them at a particular line, at a particular location. Okay, and if I take a small element somewhere here, that element has sigma 1 maybe, and it has sigma 2 in these directions. Okay, so that kind of a situation. And let's say we take a situation where both F1 and F2 are equal. So F1 is equal to F2, and the geometry is also squared. So basically, as a result, your sigma 1 is equal to sigma 2. If that is the condition, then within this geometry, if I extend it, where is the line sigma 1 is equal to sigma 2? That is this line, right? Sigma 1 is equal to sigma 2. When will the failure take place? When sigma 1 reaches Fy, at the same time, sigma 2 will also reach Fy. What does that mean? Now, think about it for a minute. I had this element here, that I'm drawing here. I had already pulled it by Fy. When I pull it by Fy, almost Fy, let's say, how far is it from yielding? I've already pulled it by Fy, it's about to yield, okay? It cannot take any additional stress without yielding. Now, if I ask you, how much stress can I apply in this direction before it yields? Okay, it's almost ready to yield. You can, to be more precise, you can say it's almost ready to be Fy. Now, how much stress I can apply here before it yields? What will be your answer? You want me to open the slide again? What happened? Are you guys disconnected, or you can hear me, right? Hello?
Yes, yes, we can hear you.
Yeah. So please answer, no? I'm just drawing that geometry again here for your reference. So your sigma 1, so this point is Fy basically. This point is also Fy. I have already pulled sigma 1 to be equal to Fy. Almost, so I'm almost at this point. I've started from here, 0, 0, and I've pulled it almost to this point. Now I'm asking, how much can I travel in this direction before I yield? Or before I reach the yield point? Again, Fy. Right? So how interesting is that? I was already at the point of yielding, but as long as I'm pulling in the perpendicular direction, I can again pull it by Fy without yielding, right? So it has still another Fy capacity in reserve before it yields, but not in the same direction, of course, in the perpendicular direction. Okay, is that clear to everyone? It can be derived from here, right? So sigma 1 is equal to sigma 2. You put here sigma 1 is equal to sigma 2. So this will become 0. Sigma 3 was anyway 0. So sigma 2, so maximum of sigma 2 is equal to Fy. So sigma 2 will be Fy, even though your sigma 1 was already Fy. Fine?
Yes, sir.
Now, let's think about another possibility. Sigma 1 is equal to minus sigma 2. This one was the possibility where sigma 1 is equal to sigma 2. The other possibility can be sigma 1 is equal to minus sigma 2. Or sigma 2 is equal to minus sigma 1. That is easier to follow. So again, same element, but instead of, let me draw it in the bigger picture also. So you had F1, and then you had F2, and F1 or F2 is equal to minus F1. Okay. So now what is happening is that I have applied sigma 1 already. Sigma 2 is acting opposite of sigma 1. So sigma 1 is tension, so sigma 2 is compression. Now, in the same geometry, which is basically defining my Tresca yield criterion in a biaxial situation. Fine. I have already pulled my material all the way to yield point. Let's say sigma 1 is already all the way to yield point. This is already up to yield point. Now, the question is, I am going to pull in the perpendicular direction, that is sigma 2 direction. By how much? But this time, instead of going up, I want to go down. Right? So how much sigma 2 can I apply before it yields?
0, sir.
0, sir.
0, sir.
Right. Very good. Very good. Yeah. So I cannot apply any additional sigma 2. Right? So that is interesting, right? Now, if you are, or in other words, if you are already at sigma, so I should not probably say sigma 2 is equal to sigma 1. That is a different condition. Sigma 1 is equal to sigma 2 was this line, but sigma 2 is equal to minus sigma 1 is this line. But the example that I just gave you is slightly different one. So in this example, first you had pulled sigma 1 is equal to Fy, and then you want to apply sigma 2. You cannot apply any additional sigma 2. Now, if we think of the possibility of sigma 2 is equal to minus sigma 1, then the line will be here. Right? So if sigma 1 is equal to minus sigma 2, how much sigma can you apply before it yields? This way or this way?
Fy by 2.
Fy divided by 2. Exactly. So sigma 1 is equal to minus sigma 2. Then sigma yielding will be at sigma 1 is equal to sigma or minus sigma 2. Fy. Okay. So either it's on this side or on that side. At Fy by 2. Sorry. At Fy by 2. Fine. What is that situation called? We just learned, right? Tresca criteria is Fy by 2 is the maximum shear stress. So when sigma 1 is equal to minus sigma 2, that is when you have a situation of pure shear stress. Mohr circle, your sigma 1 is here, and your sigma 2 is exactly opposite of sigma 1. Then you have the condition of pure shear stress. When you have pure shear stress, then the difference between sigma 1 or whatever this length is, that length will be like equal to shear stress, and that is equal to Fy by 2. So that's why you have failure at Fy by 2. Okay. So from here, if I ask you, if I have an element which has a shear stress of only shear stress acting on it. Sorry. It has only shear stress of tau acting on it. Okay. According to Tresca criterion, when will it yield? At what value of tau will it yield? In the third direction, there is no stress, only in biaxial situation. Only tau is acting, like so. Okay. At what value of tau will it yield? If I do a uniaxial tension test, it yields at Fy tension. Let's say 250 MPa. It yields at 250 MPa tension. At what value of tau will it yield? I think I have just given all the answers here. You have to, first you need to look at the Mohr circle, this tau, right? Then you look at the corresponding sigma 1, sigma 2. Then you look at this condition, sigma 1 is equal to minus sigma 2, and at what value of sigma 1 minus sigma 2 it yields. At what value of tau will it yield?
Fy by 2.
Fy by 2, sir. Fy by 2.
Fy by 2, yes, 125. So if 250 was the yield strength, then it will yield at 125 tau value. Okay, how? This is shear stress state. From this shear stress state, that is pure shear, right? So the corresponding Mohr circle looks like this, which is between sigma and tau. You can see the screen clearly, right? It's not too small for you to see. Is it?
Yes, sir.
Yes, sir.
It's readable, right? It is legible. So in that Mohr circle, you have this state, and in this particular orientation, you are here and here. So these are the two 90-degree angle planes, right? Tau and minus tau. So one of them is tau, the other one is minus tau, or you can call whichever one you want. Then the corresponding principal stresses will be sigma 1 and sigma 2, and they will also be equal to tau. right? And what it says is that principal stresses sigma 1, and you have condition where sigma 1 is equal to minus sigma 2, so tau and minus tau. And when they are equal to Fy by 2, that's when the yielding takes place. As per Tresca criteria, we have just derived that, right? So basically, Tresca says that the yielding takes place when the shear stress is equal to half of Fy, maximum shear stress. And in pure shear stress condition, that is what maximum shear stress is. That's what Tresca said, right? Maximum shear stress is half of Fy. And when you have only shear stress in a single plane and no other stress, then that stress is maximum shear stress. That is half of Fy. Fine. Other conditions can be, I'll just do one more example here. When sigma 1 is equal to sigma 2 is equal to sigma 3. Okay. Then when will the metal yield? As per Tresca criteria. So when it will never yield. Very good. So sigma 1 is equal to sigma 2. This will become 0. This will remain 0. This will remain 0. So you will always stay at 0. You will never go beyond this 0 point. You will never move out of this 0 point. So, and as long as you are within this geometry, it never yields. Okay. Then, of course, when they did a lot of tests on the Tresca criteria, they found that it does not always fit perfectly well with the experimental data, and they came up with some improvements over this one. And one such improvement was proposed by von Mises, and that has become a very common name now in mechanics. So von Mises criterion is another criterion which is basically also known as von Mises criteria often, and even this stress component is known as von Mises stress. But it is also dependent on shear stresses. It also depends on how much shear stresses are there. But instead of just looking at the shear stresses, it looks at the shear energy or distortion energy in the system. And what it says is that when the distortion energy, which is also the shear energy, right? So when the distortion energy reaches a particular level, that's when the yielding takes place. Okay. So instead of just saying stress reaching a particular value, it says, or maximum shear stress reaching a particular value, it says total shear distortion energy reaches a particular value. That's when the yielding takes place. And why? Okay, and this is the expression for that limit state or that yield criterion. Again, you can see principal stresses sigma 1 minus sigma 2. Same thing that we were doing last time, sigma 1 minus sigma 2, but earlier we were taking mod and then we were taking maximum. Now what he is doing is, what von Mises proposed is that you do square. And why are you doing square? Because you are calculating energy. So energy is nothing but stress multiplied by strain, correct? And strain is nothing but stress divided by shear modulus. Okay, if it's not clear, I'll maybe write it. If I draw a stress strain plot, okay, if I want to calculate how much is the energy absorbed or energy, potential energy stored in a material when it undergoes a particular level of sigma, the energy will be the area under this curve, right?
Yes, sir.
So energy will be equal to, we can take half, because multiplied by sigma, let's call it sigma 1, and let's call it epsilon 1. Sigma 1, epsilon 1, correct? What is epsilon? Or if it is if it's a shear stress, if it's a shear stress, then we will call it
Shear strain.
yeah, shear stress and shear, sorry. We'll call them shear stress and shear strains. We'll call it tau, call it tau 1, call it gamma 1 and gamma. So energy will be equal to tau 1, gamma 1. Okay, and tau 1 is fine. Gamma 1 is nothing but tau 1 divided by, what is that?
G.
G, right? Shear modulus. So basically I have half G tau 1 square. So half and G are some constants. They can go to the other side. So when I say energy reaches a particular value K, that particular value of energy is K. So I can always say 2GK. That is a new constant. I can call it K1 is equal to tau 1 square. Fine. So therefore, for the energy term, you get tau 1 square. And what he says is that, so this is tau 1, 2, this is tau 2, 3, this is tau 3, 1. Maximum stresses, maximum shear stresses. So he says that, okay, you take maximum shear stress in 1, 2 plane, squared it. So that is strain energy or distortion energy for shear strain in 1, 2, distortion energy in plane 1, 2, 3, and distortion energy in plane 3, 4, 3, 1. You add all of them, and that should be a particular value. That is 2Fy square. And this 2Fy square you can check from uniaxial test. Okay. So 2Fy square, it's not like he proposed it. He just said it remains always, this energy level always reaches a particular point. That's when the yielding takes place. Same thing in uniaxial test, same thing in biaxial test, triaxial test, no matter what. Okay. Similar to Tresca criterion. Now, if I plot this geometry, so this is obviously an ellipse between sigma 1, sigma 2. So if I'm ignoring sigma 3 terms here, I've got an equation of sigma 1 square plus sigma 2 square and so on. And if you draw it in sigma 1, sigma 2 plane, you will get an ellipse like this. Okay, that ellipse you can see here. This kind of, this ellipse. This is defined by this equation, sigma 1 minus sigma 2 squared plus sigma 2 square plus sigma 1 square. That is equal to 2Fy square. Okay. And as you can see very clearly, this is the von Mises criteria in a biaxial state, that is sigma 1 and sigma 2 are non-zero. And this is the Tresca criteria in a biaxial state, when again sigma 1 and sigma 2 are non-zero. Okay. And they are very close to each other almost, right? Except in some conditions. So when sigma 1 is equal to sigma 2, as you remember this example, when sigma 1 was equal to sigma 2, we were moving in this plane, correct? The predictions of von Mises is exactly same as the prediction of Tresca. Right? However, when sigma 1 is equal to minus sigma 2, then we were moving in this plane. So our Tresca was saying that sigma 1 or sigma 2 should be equal to half of Fy. Right? This value was half of Fy. But von Mises says that it can be slightly larger. And how much is that? That turns out to be, yeah, tell me. Fy
by root 3.
By root 3. So that is the condition of pure shear state, right? This is the pure shear stress condition. This line corresponds to pure shear stress, where that's when your sigma 1 is equal to minus sigma 2. And that pure shear state, the yielding happens when the stress is equal to Fy by root 3, or shear stress is equal to Fy by root 3. And this is what has been adopted into the Indian code also. So if you look at IS 800, you all have a copy of IS 800 with you? Last time I had asked.
Yes, sir.
Right?
Yes,
Yes,
sir.
sir.
Correct. So all this discussion, just to bring you this point, because you may have to answer it at some point. You should know where this came from. So for shear strength, if you see, you have to go to the beam. Chapter 5 is so this is tension. In tension you will have shear. So I'm giving you just one example. Block shear, right? Correct. So here, in case of a block shear failure, you have these values, Fy divided by
Root 3.
How to highlight it? Highlight this term Fy divided by root 3. It's not a text. Or Fu divided by root 3. This part. Anyway, I hope you can see it now, right? So this Fu divided by root 3 and Fy divided by root 3 are coming from this von Mises criteria of metal failure. Okay. So what is evident from here is that the Indian code is not using the Tresca criteria for defining failure in shear conditions. It is using von Mises criteria. So I can ask you a question based on whether it is based on von Mises criteria or Tresca criteria. So if it were based on von Mises criteria, the yield strength should have been Fy by 2, but it is actually Fy by root 3. Okay, and that is what is derived here in the next slide. Is Fy by root 3 here. So I'm sure you can go through these examples. I don't have to go through one by one. Okay. If you have any doubts, you can always ask me. Any doubts so far? Any doubts? Is my pace sufficient? Am I going too fast? Am I going too slow? If you have any comments, you let me know. If you have any questions, please ask some questions. No? Okay. Feel free to ask. Yeah? Just interrupt me and ask me whenever. So just say, sir, I have a question, then I'll complete that topic, whatever I'm discussing, and then I'll come back to you and let you ask the question. Fine. So if so far I have been drawing in these slides, I have been drawing that geometry that defines the failure surface on a sigma 1, sigma 2, on a sigma 1, sigma 2 plane. But if I draw that in a sigma 1, sigma 2, sigma 3 plane, then the geometry looks like this. If you can see this hexagon, that hexagon you were able to see before also. But in case of a three-dimensional space, triaxial space, this hexagon will be stretched into a prism, right? So it will be a prism. Okay, and if I have that prism, there would be a longitudinal axis right at the center of that prism, and that longitudinal axis will be sigma 1 is equal to sigma 2 is equal to sigma 3. So now, what is that line? So let's say I have three axes, right? 1, 2, 3, x, y. X, y, z. Let's say this one. Okay. So let's say I have these three axes, x, y, and z. Okay. These are three perpendicular axes, or 1, 2, and 3. Then you can see my hand, right? You can see the fingers that I'm projecting outward. Everyone, somebody please say yes or no.
Yes, sir.
Okay. Yeah. So if I draw a line which is at 45 degrees angle from all three of them, okay, which is going like this, or you imagine any corner. I don't have a three-dimensional object with me. Imagine that you have a room, okay, whichever room you are sitting in. Imagine a corner of that room, okay, and then you think of a line and imagine that your room is perfectly cubed, and then imagine that there is a line that is coming from one corner and going and meeting the exact opposite corner through the middle of the room. Okay, so that line will be your sigma 1, sigma 2, sigma 3. If the three lines that are meeting at that corner, three edges that are meeting at that corner are sigma 1, sigma 2, sigma 3 axis respectively, then that diagonal line will be sigma 1 is equal to sigma 2 is equal to sigma 3. Okay, then you can imagine that if you put a cylinder or a prism around it, a hexagonal shaped prism around it, that hexagonal prism will represent the Tresca criteria. And if you put a cylinder around it, like here, so that cylinder is perfectly circular. It is not really elliptical. It was looking elliptical in sigma 1, sigma 2 plane. Likewise, it will look elliptical in sigma 2, sigma 3 plane. But if you look down from this axis, that is sigma 1 is equal to sigma 2 is equal to sigma 3 line, it's also known as hydrostatic axis. If you look down from there, then that ellipse, then it will not look elliptical. It will not be an ellipse. It will be a circle. Okay. Similarly, that hexagon that was kind of a skewed hexagon will be a perfect equal-sized hexagon. Agreed?
Yes, sir.
Yes, sir.
Good. So one last question. Why is this axis called hydrostatic axis? Why hydrostatic?
Because in water only, I mean, the pressure from the three sides will be equal.
Exactly. So since water cannot have any shear stress, your sigma 1 always has to be equal to sigma 2, always has to be equal to sigma 3. Okay? Right? And as a result, water that is not moving, so not hydrodynamic stress, hydrodynamic axis, it is hydrostatic axis. So in static condition, water cannot resist any shear stress, and therefore you have sigma 1, sigma 2, sigma 3 all balancing each other, and that is that line. So what it means is that basically this cylinder or this prism, this is extending infinitely in both directions. What it means is that as long as you maintain sigma 1 is equal to sigma 2 is equal to sigma 3, you never deviate away from that axis, that is hydrostatic axis, and you never have a risk of failure. Correct? Because the failure will happen only when you touch the boundaries, and the boundaries are, in order for you to touch the boundary, you have to move away from the hydrostatic axis. As long as you are within that hydrostatic axis or close to that hydrostatic axis, you'll never reach the yield. That is quite surprising, right? No matter how much stress you apply, as long as you maintain sigma 1, sigma 2, sigma 3 values to be equal, you never reach the failure. Okay, and of course these theories, they don't have any fundamental basis. These are based on some experimental work, and whatever this theory comes out with depends on in what range of the sigma 1, sigma 2, sigma 3 these tests were done. Okay, so don't start to hypothesize and say that, okay, what happens if I put it right at the center of Earth? There is so much of sigma 1, sigma 2, sigma 3 acting, still the metal will yield. Of course, it probably will yield or it will melt or whatever, but that's not what these experiments were conducted on. Okay? Okay, any questions now?
Hello, sir.
Yes.
What is that high plane?
What is that high plane?
High plane, high.
Yeah.
Yes.
This one, the blue one.
Yes. Yes.
Deviated plane. Yeah. So basically, what it says is that one way to move. See, the movement you can define in two ways. One is that you are moving only along sigma 1, sigma 2, sigma 3 equal to all of them equal to each other. That is your hydrostatic plane, hydrostatic axis. And the other one is deviatory plane. So as soon as you move away from it, right? So let's say I move from 0, 0, 0, I move from 0, 0, 0 to, I move up to this point on the hydrostatic axis. Then I can move on that deviatory plane. And as I move on that deviatory plane, then I start to increase the von Mises or Tresca stresses, and I get closer to the failure. So movement on this plane makes me susceptible to failure. That is movement in the direction of this plane. But as long as I keep moving perpendicular to this plane, I don't have the risk of failure. That's what this is, deviatory plane. So deviation basically means when your sigma 1 stops becoming equal to sigma 2, that's when you are deviating from that, right? Or when sigma 2 stops becoming equal to sigma 3, that's when you are deviating from it. So that's why it's called deviatory plane. Okay. Yeah. So for metals, these two criteria are often used, Tresca and von Mises, and von Mises is much more frequently used. For other types of materials, there are some other materials which have hydrostatic pressure dependent properties, right? So this particular material, like these two models, they had this shape of this cylinder or the shape of this hexagon did not change as you moved along this axis, the longitudinal axis, right? Hydrostatic axis. So the failure surface did not depend on the hydrostatic pressure. There are other materials such as granular materials like soil and concrete, where the shape of this circle, the size of this circle rather, or the size of that hexagon. Okay, this is not exact perfect hexagon. It has some peculiarities, but whatever. That size depends on how far along on that axis you are. So if you go to the tension side, then that size becomes very small. Then you can have very small, like even with the smallest amount of shear stress, you can have a failure. That would be somewhere here. So let's say this circle is our limit. We are using the Mohr Coulomb criterion. Mohr Coulomb criterion you must have heard of in soil mechanics, right? It is often used in soil mechanics, Mohr Coulomb criterion. So let's say you reach a particular level of tensile stress, that is your cohesive stress, and at that point, that is the limit, and let's say that is that point. So then as soon as you introduce any shear or without any shear also, you are already at the yield point or the failure point. But as you keep moving in this direction, you have much more liberty because now you have much bigger surface to work with. Okay, so you have this kind of a conical shape. So these are called Drucker-Prager and more Coulomb, and I'm sure both of these will be taught. This is something that you just have to go through on your own also. So there are various types of cross sections which are often used in steel construction. There is a message. Somebody has typed some message from me. What is that message from? Okay. If anybody has a question, you can just give me a shout. Just say that. So
Hello.
yes.
Sir, I do have a question.
Yeah.
Sir, you said that the IS code has accepted von Mises criteria. Is there any
Yes.
reasons for why? Is there any reasons why Tesca is not? Implemented?
Yeah. So yeah, one Tesca is older, and then it was, of course, that model was improved on by von Mises. So von Mises matches much better than Tesca in real experiments.
Okay. Okay, sir. Thank you. Sir.
So von Mises was a more a relatively advanced model. I mean, even that is like 100 years old. But
Okay. Thank you, sir.
Sir,
Any other questions? Yeah.
So these both are completely empirical, or do they have any theoretical?
No, they don't have any theoretical basis. They are empirical only. No, I mean that distortion energy and so on. Those things are like kind of made-up quantities that they have. Somebody hypothesizes that okay, maybe distortion energy that is stored in the material, that is what is going to govern the failure. And then they come up with this criteria. They test it with a large number of experiments, and they found okay, this seems to be matching. Purely empirical.
Okay, sir.
So you said before that the circle and that hexagonal shape for some material keep on reducing.
Yes.
Sir, can you explain it one more time? Why it reduces in some material like soil and concrete?
Okay, so see, I'm not a materials engineer or material scientist, so I will not be able to explain it to that level. Maybe if you talk to somebody from material science background, they will be able to tell you at a deeper level. What happens is that many of these materials, which are friction dependent, right? So unlike metals have, so if I take a piece of metal, mostly steel particularly, whatever tensile strength it has the same compressive strength. So if it yields, if you take a chunk of steel, you pull it in tension, it yields at a particular stress. You push it in compression, it yields at the same stress in compression. Okay, and that is clearly visible in this kind of a behavior. So you move in this direction, right? So whether you move in this direction or you move in this direction, it has the same behavior. However, for soils or concrete, we all know that we'll take example of concrete, for example. So concrete, we know, has a higher compressive strength than tensile strength. Now, if you ask me why does it have that, the one reason I can give is friction, because friction works when you have compression, right? Friction doesn't work when you have tension, right? So you can explain some of it through friction, but I don't know whether that is sufficient explanation or not. But as long as you accept the fact or the observation that concrete and soils, they perform much better, they have much higher strength in compression than in tension, then what happens is that in this direction you are applying compression, and in this direction you are applying tension. So as you keep pulling it in tension, there will be some point where it will rupture, or when it will fail or break. But in compression, as long as you keep applying compression, that is equal in three directions. Okay, so you take a block of concrete and you press from three sides by equal force. Okay, let's say take a sphere and put it in deep water. Okay, and keep going deeper and deeper in water. So you are applying sigma 1 is equal to sigma 2 is equal to sigma 3, equal pressure. And no matter how much stress you apply, according to this theory, it will never fail. Okay, but if you apply sigma 1 is equal to sigma 2 is equal to sigma 3 in tension, that is moving in this direction, then it will fail at some point. And that because concrete and soil and all these materials, they have this kind of a peculiarity where they behave differently in tension than in compression, right? Because of that, you have to come up with a model which treats compression differently and tension differently. So in compression, as you keep applying more and more and more hydrostatic pressure, that is, as you keep moving further and further up on this axis, you're applying higher and higher hydrostatic pressure, your strength keeps increasing. That is, how much you can move away from the centroid before you reach the failure point keeps increasing. You move further up, then you will be able to move further away. Okay? Right? So basically, as you're applying more and more hydrostatic pressure, you are putting more and more, try to think from the friction point of view. So you are adding more and more normal stress. And as the normal stress or normal force increases, your friction required to make the material slip will increase, or the friction force required to cause the shear failure will increase because of the higher normal stress. Vishal, is that good enough explanation for you, or does that make sense?
Yes, sir. Yes, I understood.
Yeah. Anybody else? Achha, that was Manik you asked. Okay, sorry, I thought it was Vishal. Anybody else? Any other questions? Okay, so quickly I'll go through these two slides and we'll start from the residual stresses in the next slide. So there are various types of cross sections that are available. You can go to two primary codes. One is this IS 808. You must go to this one once. I'll take you to this one quickly. And the other one of importance is IS 12778. Okay, and these sections, these two codes give you most of the cross sections that you will come across ever. Okay, in your regular practice. So let me take you to IS 808 quickly. I had that open somewhere. Yeah, here it is. So this is IS 808. This is a very old version, 1989. I don't think it has been revised lately. So it gives you a number of cross sections. You can see my screen, right? All of you can see my screen? Yeah. So it has ISJB cross section, ISLB cross sections, ISMB cross section. You all know about ISMB, Indian Standards Medium Beam, Indian Standards. W stands for Wide Flange Beam, Indian Standard Light Beam, Junior Beam, right? And likewise, you have columns or heavy sections, ISSC, ISJC. These are channel sections. Okay. ISSC is not a channel section, even though it has C at the end. ISSC. It actually corresponds to column, stands for column. Okay. Whereas ISJC is junior channel. Okay. So a typical column section has this kind of a geometry where B and D proportion, let me go one by one. Okay. So you are all familiar with ISMB sections, right? So ISMB 200, for example, a very commonly used section. It has a depth of 200 millimeter. You can see. It has a depth of 200 and width of 100. So the total depth of, this is the total depth, that is 200, and total width is 100. Okay. But ISMB sections typically have this particular phenomenon wherein the flange is not of uniform thickness. Then in addition to ISMB, you have ISLB, JB, which are lighter sections and so on. Then you have wide flange beams also. What is a wide flange beam? A wide flange beam is basically where the proportion of D to B is changed slightly. So for example, a ISWB 150 has a depth of 150 mm, but a width of 100 mm. Likewise, ISMB 200 had a ratio of 2:1. Remember that? So ISWB 200 has a ratio of 200:140. Okay, so these are wider sections. Okay, these are called wide beams. So often you may need a wider beam to be used. Also, the sections that can be used as a column more frequently are called ISSC sections. So ISSC sections have almost equal D to B ratio. Okay, so because it's better to have a column which occupies a square shape, almost a square area. Okay, so such kind of sections are used for column sections. These are not wide flange. Wide flange do not have that kind of a ratio. So wide flanges, I have WB sections, wide flange beams. These are column sections, SC sections, which are like D to B ratio is almost equal. So you can see ISSC 200, that has a depth of 200 and also the width of 200. Can see? Okay. Then you have also heavy beams, which are called HB. Then you have channel sections, angle sections, T sections, and so on. Okay. So I'm not going to go into that. In addition to that, there is another class of sections which are known as parallel flange sections. Okay. And what is fundamental difference between parallel flange and the regular IS sections is this. So our regular sections, IS sections, have this kind of a shape. Again, excuse me for the poor quality drawings. Yeah. So if you look at the flange width, it varies quite a bit. So of course there will be toe in the beginning, and there will be this kind of a radius or a fillet here towards the end. But in between also there is constant slope. Okay. And this constant slope is generated because of the rolling process. The way your rollers are designed, because this shape comes out from a rolling process, right? As I had described in the previous class. There is a roller which rotates like this, which gives this shape, right? But there are newer technologies of rolling wherein you can develop almost a parallel flange. Okay, so away from the toe and away from this fillet, in the middle portion also, here you had a slope in the middle portion, and here you don't have a slope. These two lines are equal thickness. Okay, such sections are known as parallel flange sections, and they have various advantages. Can somebody quickly tell me what is the advantage of parallel flange section? Do you have another class? Sorry, I'm already past 4 p.m. Does anybody have a class?
Yes, sir.
Okay. So then we'll talk in the next class. Okay. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.